Okay, hi guys. So in this lecture, we'll be seeing some more examples on KC and TC, and then we'll be seeing something known as um, France rearrangement. Okay, so let's get started. So we have something like this compound. Okay, we are passing HBr and CCl4 for this compound. So what will we have to determine the KC and the TC product. Okay, so let's get started with the mechanism first. We'll have something like this. Okay, and in this first, H plus would be attacked on by this carbon atom. As a result, this carbon atom would be getting positive charge. Okay, this is the most stable positive charge one can have, but we can also rearrange it something to like this and see whether this is more stable or not. Okay, if we get if we get positive charge here, then how many alpha hydrogens are for this compound? For this carbocation we have only 2 alpha hydrogen, and for this 3 plus 2 5 alpha hydrogen. So obviously this is more stable than this. So kinetically stable product would be derived from this, and thermodynamically stable product would be derived from this. Okay, and why this? Because obviously the product formed would be more stable, as this alkene is more stable than this alkene. Okay, why this alkene is more stable? Because it is also having one CH3 group attached to it, which is a plus I effect attached to alkene, which is always welcomed by alkene. Okay, so this will give me a thermodynamically controlled product would be something like this, and KC product would be, will have this as the KC product. Okay, let's see another example. We have now CH3 CH2 HBr. Again, in presence of CCl4, we have to determine the KC plus TC product. So what will happen is, let's get started with the mechanism. So obviously this carbon atom would be getting a positive charge. Why? Because it is the most stable, or it can become the most stable because when you compare positive charge on this carbon atom, this carbon atom, this carbon atom, or this carbon atom, this carbon atom suits to hold the positive charge best. Why? Because it is attached with two plus I groups, two CH3 groups rather. Okay, so we'll have something like this. Obviously it has accepted H plus, so we'll get something like CS3 here. Okay, so now this is the intermediate, and it can undergo actually rearrangement. So we can get rearrangement, or rather conjugate between positive charge and double bond. So we'll get positive charge rearranged at this, or replaced at this carbon atom. Will be getting something like this. Okay, so obviously the stability of this alkene, which would be in the product side, would be more. Why? Because of the attached two CH3 groups, wherein this alkene only one bulky group is attached. Hence this stability would be more. Hence this would be deriving our TC product, and this would be deriving our KC product. So hence we'll be getting something like Br here, CH3 here, something like this product, and this TC product would be, this would be our TC product. Okay, let's do another example wherein we have something like this product or this compound, and we are passing again HBr, presence of CCl4, determine KC and TC product. Again, let's draw the intermediate state. We'll be getting something like this. Okay, or rather plus sign would be conjugate to this carbon, to this double bond, hence would be getting something like plus positive charge here. Okay, and then we'll be getting, you can check if we can make a different intermediate by replacing by having the resonance in the intermediate state. So I think both the two structures are same, hence we will have similar KC and TC products. TC product in this case would be same as KC product. Okay, let's see another example. Now we have something like this compound, okay, and we are passing n bromosuccinic acid on this. So we have to determine the Kc and Tc product in this case. So let's actually discuss this mechanism of NBS, so which is a free radical mechanism. I hope you remember. So what will happen is, this is a compound, original compound we are having. So what will the first step? First step would be Br would be actually getting in presence of H nu and breaking itself into 2 Br dots. Okay, next what will happen is, in the second step, obviously this alkene would be passed on with Br dot, and it will take the H dot from the alkene, and as a result we'll be getting dot here. Okay, now what will happen is, on this dot we can have either, so on this dot, this is in the intermediate state. Okay, this can actually undergo rearrangement or other conjugation, as we can get something like this in the intermediate. Now obviously this dot is, or this free radical at this position is having how many alpha hydrogens? 2 alpha hydrogens, and at this position we are having 0 alpha hydrogens. So obviously this would be determining our Kc product. Okay, but if you see the overall product stability, obviously this alkene, it would be more stable because of more number of substituents attached on both the sides or on both the carbons of alkene. Hence this would be more stable, hence this would be deriving our Tc product. In this case, Br dot would be attaching here. I hope you remember that we generated 2 Br dots, so 1 Br dot is consumed here and another one is consumed here. Okay, this would be the Kc product and this would be the Tc product. Okay, so for some of you who maybe are still in confusion as to how this first step came into the picture, how the Br2 actually came to the picture. So actually what happens in NBS is, this is the structure of N bromo, or rather NBS. So in presence of HBr, what actually happens is, N bromosuccinamide attacks on this H plus, okay, and as a result we get positive sign here, and then what happens is plus Br minus, or rather actually the Br minus from the HBr actually attacks on this Br, and this bond is taken back by the N plus, and as a result we get something like NH and Br2, and then this Br2 is passed on in H nu sunlight. Okay, so just to write a single liner about the mechanism of NBS, that NBS is used to replace alpha hydrogen by a halogen and by a free radical. NBS is used to replace alpha hydrogen by halogen with free radical mechanism. Okay, so with this we come to an end of this lecture. We'll be taking up the Franz rearrangement in the next chapter, or in the next lecture rather. So till then, good luck and goodbye.